Okay, here we are now with example problem 4. So this is our water balance example 4, and this time now our control volume is going to be the water that is present in the soil pore spaces, which we call soil water, soil moisture. So this is, we're going to be looking at soil water storage. So the problem you're given is you've got a gentle hill slope with an area of 10 to the 4 square meters. So 10 to the 4 is 10,000. So 10,000 square meters, which receives rain for a period of 40 minutes. So we're looking at a very short time period here, and it's during a rainstorm. So something very common with our water balance equation when we're looking at just a storm period is that we can assume that evaporation is pretty negligible because it's cloudy, it's humid, and so the evaporation rate is pretty low, and it's very small compared to the rates of precipitation that we're dealing with. So we're going to assume that we're not dealing with evaporation. So our average rainfall intensity was 30 millimeters per hour, but it only rained for 40 minutes. So it didn't actually rain 30 millimeters, right? So we'll have to calculate that. The total surface water flow, so this is what runs off over the surface during that 40 minutes, was 15,000 liters. So 15 times 10 to the 4 liters. And what we're going to make an assumption, besides just that the evaporation is negligible, we're also going to assume, because remember our control volume now is our soil, we're also going to assume that in that 40 minutes, percolation out of our soil, so that's percolation via gravity to deeper groundwater, we're going to assume that that's negligible also, because we haven't had enough time for that to happen. And what we want to calculate is the change in the soil water storage that occurs over that 40-minute time period. So first, let's start off, of course, with drawing our picture. So we have a gently sloping area. So I'll draw a little tree to demonstrate this is that's our surface, right? The surface of the land, and we're going down some depth in the soil. So that's our control volume. So we have precipitation that falls on the surface, but we have to be careful because that precipitation is not actually an inflow to our control volume, right? And then we have our surface runoff over the surface. And then we have our infiltration from the surface into the subsurface. Now that is our inflow into our control volume. And we need to figure that out in order to actually do our water balance on our soil water. So what we're looking at, our control volume, is the water that's stored in the soil under this 10,000 square meter area. So we'll set this A. So let's list our givens real quick. All the things we know. We know that our time period, delta T, is 40 minutes. We know that our rainfall intensity, which we'll actually call little I, is 30 millimeters per hour. So we're actually going to have to calculate P, the millimeters, over our delta T, right? And let's see, we know that our surface runoff, which we're calling R, is 15 times 10 to the 4 liters, and that was over that 40-minute period. And we're assuming that ET is about 0 and percolation is about 0. So I'll go ahead and draw those on here, but I'll say that ET is about equal to 0. And percolation here would be an outflow from our storage, our soil control volume. So percolation would be an outflow, but that's about equal to 0. All right, so our water balance for our soil, what we want to find is the change in storage of the soil water. And we're going to call that delta S. So there's our delta S in our soil. All right. So let's set up our water balance equation, our usual in minus out equals delta S. In this case, our in is our infiltration, and our outflow is 0. We don't have any outflows, and that's going to be equal to our change in soil storage. So basically, all we need to do is figure out how much water infiltrated, and that's going to tell us the increase in our soil water storage volume, the change. So how do we figure out the infiltration? Well, now we have to look at a water balance on the surface. So let me write up here, this is the water balance equation for soil water. And if we think about what's going on the surface, we have precip coming in, we have runoff going out, and we have our infiltration soaking into the ground, and we have no storage. So our infiltration is just going to be the difference between the precipitation and runoff, right? So what infiltrates is what doesn't run off, or more appropriately, we should say what runs off is what doesn't infiltrate. Because when it precipitates on the surface, the first thing that happens is the water is going to soak into the soil. And once the precipitation rate overwhelms the infiltration capacity of the soil, then we actually get runoff happening. So what doesn't infiltrate runs off. So our infiltration is going to be the difference between what precipitates on the surface and what runs off on the surface. So infiltration is going to be equal to our precip minus the runoff. So we have to figure out what is our precip. So our storm precip P is going to be equal to that intensity of 30 millimeters per hour times the time period of our storm, 40 minutes. So our P is going to be equal to 30 millimeters per hour times 40 minutes, and we'll have to divide by 60 minutes per hour to get that those units correct. So let's see what we end up with for units here. Our hours cancel, our minutes cancel, and that'll give us how many millimeters, but then we have to convert that there are 1,000 millimeters per meter because we want to have those units in meters. So what we end up with is that our precipitation over the storm period is 20 millimeters, which is 0.02 meters. All right, the next thing that we need to do is to convert Q from, we're calling it R, our runoff. Convert R into, and actually we're actually going to go ahead and use millimeters for our units here. So we need to convert R to millimeters of runoff that occurred over that 40-minute period. So R is 1.5 times 10 to the 4 liters, and there are 0.001 meters cubed per liter. And so that's going to give us a volume of water applied over our area. And we're given that our area is 10 to the 4 square meters. So 10,000 square meters, which is a hectare. So we also need to divide this by the area to get our units of depth, because we want to represent this runoff in units of depth. So we have, what we're going to have here is cubic meters. So we're going to divide by the land area over which that total volume of water, we're going to spread it out, and we're going to figure out what depth of water became runoff. So this is going to be, let's do it this way. Divide all of this by 10 to the 4 meters squared. And what we end up with is 0.015 meters, which is 15 millimeters. So now we know P and we know R, so we can figure out our infiltration is 20 millimeters minus 15 millimeters, which is 5 millimeters. And we know that our infiltration is equal to our change in storage. So our change in storage is 5 millimeters, and this is over our storm period. Delta T is 40 minutes. Okay, so let's review what we've done here. So I feel like I went really fast through that. So we know that over the 40-minute period, we got 20 millimeters of rain. It rained at a rate of 30 millimeters per hour, but it only rained for 40 minutes. So that worked out to 20 millimeters of rain over this hectare of land. 20 millimeters of rain over a hectare for 40 minutes, over a 40-minute period. And the amount of water that ran off over the surface, because it didn't infiltrate, works out to be 15 millimeters of depth of water applied over that hectare. And that results in a total volume of 15,000 liters of water. So if you have 15 millimeters of water over a hectare, it works out to 15,000 liters. Okay. So we have 20 millimeters that precipitated on the land surface, 15 millimeters ran off, so that means that 5 millimeters infiltrated. And because we have no outflows from the soil moisture, that means that the storage volume of soil moisture increased by 5 millimeters of depth. All right, that's our last water balance example problem. Email me or let me know if you have questions.